But, and there's ways to solve problems like this using the negative exponents, but I find that it's pretty challenging to try to manipulate the exponents the way you need to in order to do it that way. So I think that it's a simpler process to just write these as fractions with positive exponents and then clear fractions. So we know that we can't write a single fraction because we have two separate terms with different exponents. So that first one, 7x to the negative 1, is the same as 7 divided by 1 factor of x, right? That's what a negative exponent means. It means you're dividing by multiple factors rather than multiplying by multiple factors. So we have 7 divided by 1 factor of x. And then 30x to the negative 2 is 30 divided by 2 factors of x. So 30 divided.
So 30x squared.
No. So the 1 over, like, you want to try to get away from just, like, using the rule as written. Like, when it says x to the negative n equals 1 over x to the n, what it means, it's, like, really the only way to write this symbolically without, like, writing a paragraph. But what it means is if you have x, like, to the third, that's 1 times 3 factors of x. And so if you have x to the negative third, or sorry, that's a 3. That means do the opposite of multiplying by 3 factors of x, which is to divide by 3 factors of x. So it's 1 divided by 3 factors of x. And that's how they get the 1 over whatever. But if the coefficient here isn't 1, if it's like 20, then instead of 20 times 3 factors, or 1 times 3 factors of x, that would be 20 times 3 factors of x. And if it's 20 here, instead of 1 divided by 3 factors of x, it's 20 divided by 3 factors of x. So you don't want to just use that rule as it's written. Like, we need a symbolic way to write, like, that we're just dividing by multiple factors, and so it's written that way, but that doesn't mean that it's always going to look that way in the fractions themselves. So equals negative 1. And so we talked about how that last problem, we didn't have to worry about restricted values because there wasn't any division or square roots. In this problem, there is division, right? It doesn't look like division initially, but we want to start recognizing negative exponents as division. So if we write them as fractions, we see that we have to deal with the fact that we might get a denominator of 0. So our LCM is x squared, and that means that our restricted value is just 0, so x can't be 0. So from here, I'm just going to clear fractions, so I'll multiply all terms by x squared over 1, because that's my LCD. So we have x squared over 1 times 7 over x minus x squared over 1 times 30 over x squared equals negative 1 times x squared. So in that first term, just 1 factor of x cancels, so I end up with 7x. And that second term, both factors of x cancel, so we end up with 30. And then nothing cancels over here, so we get negative x. So then I notice that I have 2 terms that contain the variable. That's my clue that I have to solve it by factoring, so I have to get a 0 on one side. You can't isolate x unless you can get a single term containing x on one side and a constant on the other. So if you have 2 instances of your variable and you can't combine them, then you have to get a 0 on one side. So I'm going to add x squared to both sides because that'll make that coefficient positive and get me my 0. So x squared plus 7x minus 30 equals 0. I can use the shortcut to factor this guy because my leading coefficient, the coefficient in front of x squared, is 1. So this is plus 10 x minus 3. So x plus 10 equals 0, x minus 3 equals 0. x equals negative 10 and 3. And both of those are valid solutions because neither is a restricted value. So it looks a little bit different. Just try to remember that you can make any rational function, any function that has fractions, into a polynomial function just by clearing fractions. So if you can remember to write these as fractions, then you just clear them, and then we're right back where we want to be to do a basic factoring problem. So another one that looks a little bit different than what we've seen before. So these are all just kind of like one-offs of things we've done before. So we're using the same skills. They're just like a little bit more involved. We have to put a little bit more together. So another one would be like, what did I do? X squared times x minus 1 to the third minus 9 times x minus 1 to the third equals 0. So when I initially look at this, I notice that I definitely have more than one instance of my variable, right? I'm not going to be able to combine everything to get like a single term that contains x. So I'm happy I have a 0 on one side. I'm going to keep it that way. And then the other side I want to be factored. Is that left side factored already? So remember, we know it's a product if the only operation outside parentheses is multiplication. Is that the case here? No, there's subtraction right in between those two terms. So we really have two terms here, 1, 2. So if I have any hope of factoring this, I would either need to distribute all that or factor out a common factor. I don't know about you, but I do not feel excited about the prospect of distributing all that and multiplying x minus 1 by itself 3 times. So instead, I'm going to look for common factors. Is there a common factor in the two terms?
X minus 1.
So I'm going to pull that out. And then the first term, I'm left with x squared. There's subtraction between my terms, and then the second term leaves me with a factor of 9. And then when I look at this, x minus 1 to the third can't be factored anymore because it's really just x minus 1 times x minus 1 times x minus 1. And there's no exponents inside the parentheses, which means I can't factor that part of it. Whereas x squared minus 9, I have an exponent inside the parentheses. That's my clue that I need to think about if I have to factor that, or if I can factor that or not. In this case, both terms are perfect squares, and it's a difference, right? Subtraction between them, that means that it'll factor. So we have x minus 1 to the third times x plus 3 times x minus 3 equals 0. So then from here, I want to set all my factors equal to 0. Technically speaking, I have 5 factors, right? I have 3 factors of x minus 1, and then a factor of x plus 3, and a factor of x minus 3. But if I write out 3 factors of x minus 1, and I have x minus 1 equals 0, x minus 1 equals 0, x minus 1 equals 0, do you guys agree that that's just going to give me 1 3 times? So if 1 is a solution, like it's a solution, I don't need to write it 3 times until you talk about multiplicity, but we won't worry about that yet. So I'm not going to write that out 3 times. I'm just going to say that if x minus 1 to the third is equal to 0, that's equivalent to saying that x minus 1 is equal to 0. And you could even skip straight to x minus 1 equals 0 if you want, right? The only thing you can raise to the third power to get 0 is 0. And then I'll set my other factors equal to 0. So x equals 1, x equals negative 3, and x equals 3. And again, I have no extraneous solution or no possibilities of extraneous solutions. Solutions that I have to throw out because there's no division in this problem and there's no square roots in this problem. So as we keep going, as we learn how to solve more and more different types of equations, it becomes important to think about those things every time, right? Is this a type of equation that might have extraneous solutions? And the way we identify that is if there's an operation with a restriction. So for us right now, that just means division or square roots. None of those exist here, so all my solutions are good. Yes?
Can we do one with where x minus greater than -1? Like x minus 2 or x minus whatever to the cube.
You mean like that's not a 1? Oh,
Yeah,
it doesn't
it's not
matter if it's a 1.
So it's always just going to come out as.
So if you have anything raised to the third power and it's equal to 0,
So you can cube root it and then you get 0.
I'm not cube rooting it. I'm just saying that if I multiply something by itself 3 times to get 0, that thing has to be 0. Right? Like the only thing you can multiply 3 factors of to get 0 is 0. Like the only way, like if I have something like x to the third equals 0, if I have something like that, well, I have to, in order to get 0, I have to have one factor of 0, right? So one of these has to be a 0. And since they're all the same, that means they all have to be zeros. Right? That, like, the only thing you can raise to any power to get 0 is 0. So it doesn't matter what's inside the parentheses. We didn't use the numbers inside the parentheses to conclude that that, like, chunk is equal to 0. So, like, if that was a 2, we just end up with x equals 2.
And if it says to simplify it, we just x minus 1, x minus 1, x minus 1. That's it. Like if the question says to just.
So you mean if you were just given, like, this and they asked you to simplify it?
Yeah.
Yes, you would just multiply it. So you'd multiply x minus 1 times x minus 1, put that in parentheses, and then multiply that by x minus 1 again. Good. Although there's a super cool way to simplify x minus 1 to any power. Like, have you guys heard of Pascal's triangle? Like, it's like this triangle that, like, it's like a 1 and then a 1 and a 1, and then you get the next rows by, like, adding. So, like, starts with a 1, then 1 plus 2 is 3, and 2 plus 1 is 3, and you can go, like, as far as you want. Well, like, the coefficients of x minus 1, actually, this one's x plus 1. You'd have to make one of your numbers negative, but, like, to the fourth. So, like, x plus 1 to the first power, the coefficients are 1 and 1, right? And then x plus 1 to the second power, you get x squared plus 2x plus 1. The coefficients are 1, 2, and 1. So to the third power, it would be 1, 3, 3, and 1. And, like, so you can do, like, x plus 1 to the, like, 20th just using, like, the triangle. It's kind of fun. It's like if you take stats and probability, then you'll have to talk about binomial distributions, which is what that deals with. But for our purposes, we won't do ones that are big enough that you have to multiply them out. So one thing that we did in this problem, sort of within the whole thing, is we solved the equation x squared minus 9 equals 0. Right? Like if you, like, just break off that piece of it. We did this problem. And we did it by factoring, which is totally fine. But the other thing we can notice here is that, remember I said that the clue that tells us that we have to factor, so we have to get a 0 on one side and factor, is that we have more than one term containing our variable. Well, here we only have one term that contains our variable, right? So it is possible for me to isolate one term containing the variable on the left and a constant on the right. So I can write this as x squared equals 9. And that works because I only have that one term with my variable in it. And then we can just use opposite operations. So the square root undoes an exponent of 2. And so I can solve this by taking the square root of both sides. But one thing to know about square roots is that every number actually has 2 square roots, right? If the square root of 9 is any number that can be squared to get 9, well, you can square 3 to get 9. You can also square negative 3 to get 9. And that's true of all positive numbers. There's always a positive and a negative that can be squared to get any positive number. So when we take the square root, we want both of them. because when we solve an equation, we're looking for any number that can be squared to get positive 9. So that's one thing you have to be careful of when you take the square root. You always get both of them when you solve by factoring, right? Because you end up with those two factors. But when you take the square root, you have to make sure that you put, like, you want the positive and negative square root of 9. So this is x equals plus or minus 3. And that plus or minus sign is just another way of writing this. Oops. It's just a way of writing positive 3 and negative 3 all in one expression instead of listing them. So the reason that this is useful is that there are equations that can't be factored, or polynomials that can't be factored, that can still be equal to 0. So there's equations that still have solutions even if we can't solve them by factoring. So for example, actually I'm going to do this one first. Let's do this one. Let's do x plus, let's do x minus 3, no, not 3, 5 squared equals 9. So when you look at that equation, how many times do you see the variable? I promise it's not a trick question. Once, yes, there's only one x. It's true that if we were to multiply it out, there'd be more than one instance of x, right? But your clue that you can use something other than factoring, other than getting a 0 and factoring, is that you only see your variable once. And so this problem, I would argue, is exactly the same as that problem. So I have something squared is equal to 9. What that something is doesn't really matter. I just know that that something is going to end up being equal to 3 or negative 3, right? So like it looks more complex, but in reality, I can undo anything to the second power just by taking the square root of it. 9 has 2 square roots. And so this just tells me that x minus 5 has to be equal to plus or minus 3. Right? So it didn't get me x straight away, but we used the same exact process because the left side was just something to the second power, which I can always undo with the square root. So even if it's not a single variable. And then we can solve from here by adding 5 to both sides. So I always add 5 on the left side of the plus or minus, only because, so if you do this, there is a strong temptation, I feel, to go like that, to go like 5 plus 3 is 8, so you get plus or minus 8. But notice that what we're really doing is 5 plus 3 and 5 minus 3, which gives us 8 and 2. Right? Do you guys see the difference? So we have to be really careful with how when we're using that symbol, like how it actually behaves. So I always write it to the left of the plus or minus sign for that reason. And then you can break this up if you want to. Like you can write x is equal to 5 plus 3 or x is equal to 5 minus 3 if it makes more sense to you to see both separately. And then that gives us x equals 8. And x equals 2. So this property that we're using is called the square root property. And like I said, you can always use it if the left side is something raised to the second power with nothing else going on outside those parentheses. And then the right side is a constant. So you can always solve use the square root property to solve equations of the form something in parentheses to the second power equals a constant. So when we say constant, that means there's no variable over here. It's just a number. So it doesn't matter what that something is. That could be like a 20-term polynomial that's like degree 30, and you maybe wouldn't be able to solve after taking the square root, but you can still take the square root of both sides to undo that something to the second. So this comes in really handy for things that we can't factor. For instance, if I want to solve x squared minus 5 equals 0, this is really similar to that x squared minus 9 that we did, but we could factor x squared minus 9 because both terms were perfect squares, right? Here, this is not factorable because 5 isn't a perfect square. And so the only way we can solve this is with the square root property. So we get our x squared on one side, and then take the square root of both sides. And so x is equal to plus or minus the square root of 5. And that's as far as we can go here. So the square root of 5, or the square root of any number that isn't a perfect square, is an irrational number. So similar to pi, right? It's a decimal that goes on forever and never repeats. And so there's no way to write it as a decimal in its exact form. So just like pi, the only way we can express it exactly is to use a symbol. And so the symbol we use is just this radical 5 to show that that's the number that can be squared to get 5. We don't go any further than that because we don't want approximate answers. That's why roots fall in. Okay, so definition we need is a number is a 0 of a function f of x if it is a solution to f of x equals 0. So basically, we call a number a 0 of a function if when you plug that number into the function, you get an output of 0. So like, if I have f of x equals x minus 2 times x plus 3, the zeros of this function are 2 and negative 3. Because if I set that function equal to 0 and solve, I get x equals 2 and x equals negative 3. So those are the numbers that you can plug into f that will give you an output of 0. So also notice that if we graph a function like this, so the graph of this function would look something like that. If I plug 2 in, an input of 2 in, and I get an output of 0, that corresponds on this graph to the point input is 2, output is 0, right? And if I plug negative 3 into that function, I get an output of 0. So that corresponds to the point that has an x value of 3 and a y value of 0. So the zeros of the function are the x coordinates of the x-intercepts of the graph. So we can make these three statements. We can say, and I'll just do it for this particular function, the solutions to x minus 2 times x plus 3 equals 0 are x equals 2 and x equals negative 3. Does everybody agree with that statement? Everybody sees how I got it without actually like writing out a solution. We all good with that? Okay. And then the zeros of f of x equals x minus 2 times x plus 3 are 2 and negative 3. And the x-intercepts of the graph of f of x equals x minus 2 times x plus 3 are 2, 0, and negative 3, 0. So all three of these statements are equivalent. So they all mean exactly the same thing. So one of the things we'll start to see as we work more in depth with functions and the behavior of functions is that there's a lot of situations where we do the same process to get something, but the thing that we're getting is different. So for instance, the process for finding the zeros of this function is the same as the process for finding the x-intercepts. I just set the function equal to 0. But, and like all of these, the zeros, those solutions, the solutions to that equation, the zeros of the function and the x-intercepts are all intimately related, but, and it's subtle, but they are different mathematical objects, right? 2 and negative 3 are just numbers. They're just single values, whereas like the x-intercepts are ordered pairs. They have an x value and a y value. You can plot them on a graph. Like you can't plot just a number on a graph, right? So even though they're really similar, they have some slight differences as far as what they actually are as mathematical objects and therefore how we use them. So one of the keys that we will work with this over this next week when we study quadratic functions is just how to like interpret things so you can get other things. So like how to interpret the x-intercept to get the zeros and things like that. And a lot of times it's just going to feel like you're doing the same thing over and over again and writing the same numbers over and over again. But they all have these like slight differences and the way we use them is slightly different. So one example we can do is like we can say like find the zeros of f of x equals x squared minus 10. Actually, no, I don't want to do that one. That's no fun. I want to do this one. 4 times x minus 3 squared minus 16. Let's do that. Make that 20. I have time for one example, so I'm trying to fit as many like things into it that you might see on your homework. Okay, I promise I won't change it again. It's 20. Okay, here we go. So I'm going to find the zeros. So the first step to finding zeros is to set your function equal to 0, right? You can't solve an equation unless there's a number on one side of it. So like, this is an equation for all the points on the graph of the function, right? We want only the points that give us an output of 0. So we have to start by setting our function equal to 0. Don't get lazy on that. I'll just make you do it again. If, like, I see this a lot, where it just starts like that, and then you get some solution. But if you don't start with an equation, then you can't find a solution to an equation. So equals 0. And then how many times do you see the variable? Just once, right? That's our clue that we don't have to factor. We can just isolate the thing that's squared. So in this case, this right here is something raised to the second power. So I have to get rid of all the other stuff on the left side before I take the square root. So I have to get that guy alone. So I'm going to add 20 to both sides. And then divide both sides by 4. So now I have an equation of the form something raised to the second power is equal to a number. And that's when I'm allowed to use the square root property. So make sure there's no multiplication or addition or anything else going on outside those parentheses before you take the square root. So we have the square root of x minus 3 squared equals, remember that every number has 2 square roots, a positive one and a negative one. And that gives me x minus 3 equals plus or minus the square root of 5. And again, we're leaving it in exact form, so you don't want to put that in your calculator. Just leave it as a radical. And so now I just have to add 3 to both sides. So I get x equals 3 plus or minus the square root of 5. And so my zeros are 3 plus the square root of 5 and 3 minus the square root of 5. And I didn't ask for it explicitly, but you can also from this find the x-intercepts. We just take our zeros and make them the x values. Yes?
Do we have to take the square root out of that equation at some point?
What do you mean take it out?
Like put that equation to our calculator?
So the only time you'll ever do an approximate answer is if it's an application. So if you had to, if I asked you for like, to maximize the area of a rectangle and you solved the equation and you got x equals these numbers, then at that point, yes, you put it in your calculator because it doesn't make sense to be like the width of the rectangle should be 3 plus the square root of 5 feet, right? So it makes more sense in applications to round your final answer, but that's the only place we'll do it.
Can we just leave your edge on the homework x equals 3 plus or minus square root of 5? Or do we have to write it out?
So you can, for the zeros, you can write it like that. For x-intercepts, you can't write like 3 plus or minus the square root of 5 comma 0, right? Because that's a single ordered pair and it's really 2 ordered pairs. So for the x-intercepts, you need to write like both of them like separately because they're 2 separate points. But yeah, it's totally fine to use the plus or minus in other instances when you're just talking about the numbers. So on your homework tonight, especially on my math lab, just be really careful as far as the difference between zeros and x-intercepts, right? It can be really frustrating if you solve the equation correctly and then like you put points where you should put numbers or you put numbers where you should put points, right? That's why we were such sticklers about writing your intercepts as ordered pairs, like when you guys were looking at graphs way back on test 1, because of these subtle differences between the two, you want them to look different so that you can recognize that they're different objects. So that's all for today. Let me give you your worksheet, and you'll be good to go.